Okay, hello. Today is Friday, October 16th, and we'll be, I think, probably finishing up the constrained optimization material. Actually, oddly enough, we're really not like so far off in the syllabus. Does anybody have a copy of the syllabus? Like, I think that we're not actually so like weirdly far off. We were supposed to be doing constraint optimization, and then after this we go into the EDMM algorithm, right?
Yes.
And we're more or less on track, which is perhaps amazing.
Yeah. Well, according to the syllabus, we're supposed to still be in constraint optimization for like the next 2 lectures.
Oh, really? So
Yeah.
I could theoretically spend an additional lecture.
Yeah.
We'll see how it goes. There's definitely stuff to cover, so maybe I'll spend more time on it. But maybe I'll jump ahead, because the next topic is, what's after this?
The EDMM algorithm.
Yeah.
Oh, but that's on the syllabus. Okay, I'm going to talk about... Oh, see, but I added... Oh, I forgot to update the syllabus. Remind me to update the syllabus again, because I added a chapter. That's well, it depends how you want to define it, but it's like, okay, so yeah, I got to update the chapter numbers, because I inserted a chapter, basically, this past summer or something like that. Okay, and so that's okay. So we will take 2 more lectures. We'll take 3 more lectures, because we'll finish up constraint optimization this lecture, and then we'll move to the plug-and-play methods. We'll do that like for maybe 2 lectures. Okay, so what am I doing here? I want to do this. Okay, what I want to do is some examples at this point. So this is actually, well, maybe since I have the projector going, I'll like talk about it. So this is the ADMM algorithm. Then I talked about this last time, and this is a proximal map, and that's a proximal map. And just to review, what is a proximal map? A proximal map is like you have this function you want to minimize, right? And you start at some point x, okay? Maybe I'll call it x prime, okay? And then what happens is that you add to this function. So this is f of x, okay? And then you add to this function a second function, and this function is like a over 2 norm of x minus x prime squared, okay? Right, because that's just the distance. It's a quadratic function of the distance from x prime, and this point is x prime, right? Does that make sense? This is like important to understand just a simple idea. So if you have any questions, stop me here, because if you have a question, it's likely other people have the same question. So then if I add these 2 functions, right? If I add these 2 functions, I get something that looks like this, right? Like that. Because this function's 0 here, right? So this is like a surrogate function. That's why it's good that we covered surrogate functions first, right? So this whole proximal map is just like another kind of surrogate function. It's a surrogate function for the function f that we're minimizing, right? So the solution then comes out to here, which I'll call x double prime, okay? So what happens is you get x double prime equals f of x prime. And what's f? F is f of x equals the arg or argmin, well, I'll do it like this. I'll say f of v. One of the things that gets a little confusing about proximal maps is the dummy variables, okay? If dummy variables throw you off, think hard on this one, because remember, I'm allowed to use any letter I want, as long as I use the same letter everywhere for that role, okay? It doesn't have to be an X. I can put a V. I could build a little happy face. I can do anything, right? So you just don't let that throw you off. So this is argmin over X. This will be f of X plus a over 2 norm of X minus V squared. Right? So the idea here is that I'm minimizing a surrogate function for the true function I'm minimizing, okay? So when I apply the proximal map, it's like one step in an iterative algorithm that gets me a little closer to the minimum, okay? One thing that's really important to understand about a proximal map, I wonder if the video is going to be dark, because what happens is that when the video is on, the automatic gain control in there changes. So I'll put this as blank. For the studio audience, you can maybe see, you may have had trouble reading this, you know, because the brightness on the camera changes when I turn on the thing. But the important thing is this, that, okay, so this is the space of solutions over here. Space of solutions. And like, there's nothing to draw, because space is like the last frontier, okay? It's like space is empty, okay? So I don't know what to draw. But then what ends up happening is there's some point here, right? And we'll call this x prime, right? And then what happens is that you apply f to x prime, and what comes out is x double prime. This, like I said, it's the simplest ideas that are most powerful. So the thing that's really important to understand about a proximal map is like super, super subtle. Proximal map takes an input, which is a point in the space, and it produces an output, which is a point in the space. So the domain and the range of a proximal map live in the same space. Okay? That's really an important idea. Why is that an important idea? Because usually when you're solving problems like inverse problems, you have data, like that's usually what I write as y. And then from y, the data, you try to produce a solution, x, right? But that's not what the idea of a proximal map is. Proximal map doesn't take in the data y and produce an output x. It takes an output, it takes a point x, and it produces another point x, okay? Now you'd say, well, that doesn't make any sense because I have to have the data. How do I do it? Well, yeah, okay, but that's not what the idea is of a proximal map. That's why I suppress the dependency on y. I'm pretending y is like a constant. I'm not even writing it down. Y is embedded in this f. So it's not a mapping from the data to the reconstruction. It's a mapping from a reconstruction to another reconstruction. That may seem like I'm beating it to death and it's uninteresting, but I can guarantee you're going to get confused about it. And the reason is this, that when you're solving problems, particularly if you're an engineer, engineers are worried about taking data and producing solutions, right? But this is not about taking the data and producing a solution. It's about taking a solution and producing another solution. So it's fundamentally different in that sense. in a very subtle way. It takes a solution and it changes it. That's kind of an interesting idea, because what happens is that I like to think of proximal maps as being like people, okay? Like people, you give them some solution and they go, well, I don't like that solution. I like this solution better, right? It's like, people like to change things, right? You give them something and then they change it in some way that they like it better. You like give them a house, they upgrade the kitchen, okay? You give them, I don't know, a document, they edit it to improve it, right? But you give them something and they produce something else that's better from their point of view. And that's what this proximal map does. It takes an input, it acts as a reconstruction. It takes a reconstruction and it produces a new reconstruction which is better than the old reconstruction. But what do I mean by better? By better I mean little f is smaller. So if I keep reapplying the proximal map, the proximal map is just a surrogate function, right? Well, it's not actually a surrogate function, that's a lie. It's the operation you get by minimizing the surrogate function. So this thing here is a surrogate function, the argument here. When you minimize it, you get a new output which is better. So we know from the whole theory of surrogate functions, if you keep redoing that, eventually you get to the minimum, okay? So that's what a proximal map is. If you keep reapplying it, you will keep getting closer to the solution. Do you have a question?
Wouldn't it be, it's closer to the solution,
It's closer to the minimum of f, I should really say.
Yeah, because the best solution is based on our prior distribution.
It's based on the forward and the prior.
Yeah. So
that's correct. That's a really important point.
Then our solution would still be terrible.
Yes, that's correct. You're absolutely right. So let's go back to the algorithm. So the algorithm is this, right? If I rewrite this in terms of proximal maps, then I'll get something a little different. What I'll do is, I need to turn this off so it doesn't. So if I rewrite that algorithm in terms of proximal maps, what I get is this. I get repeat. I get x goes to f of v minus u, and then v goes to, or is it, hold on, I better make sure. Okay, yeah, because actually if you get this backwards, it's not stable. It's like hooking your thermostat up backwards, where as it gets hotter, you raise the temperature, it becomes unstable. So you get h of v plus u. No, v, this is, hold on, yeah, v.
H is the function of the...
Oh, yeah, no, this is right. Yeah. So the input is v, and the output is x. So I had it right the first time. This is v, this is x, and this is x, and that's v. And then u goes to u plus x minus v. This is the iteration, okay? Where now, that's right now, it's going to be f of, say, v is equal to arg min over x of f of x plus a over 2 norm of x minus v squared. And h of v is equal to arg min over x of h of x plus a over 2 norm x minus v squared, like that, right? I'll erase this because okay? And both of these things are proximal maps. Okay? And that's what gets applied here, right? So what's maybe less clear is that iterating this will converge. Okay? But it's true. All right. Now, let's actually work a problem with this framework so you can see how it works. So imagine that you want to solve a problem like this. By the way, so this is, any questions? So, okay, so imagine you want to work a problem where, let's say f of x is equal to, I don't know, 1/2 y minus ax, okay? So you're trying to solve a problem where you have a linear sensor. And yeah, as I said, you're suppressing the dependence on y, which is the data, because you're kind of just assuming that's fixed. Now, and then say h of x is equal to so like, let's say h of x is equal to 0 if for all I, xi is greater than or equal to 0, and it's equal to infinity if there exists an I such that x of I is less than 0. So this is called a positivity constraint. Essentially what ends up happening is that, so let's say in 2 dimensions, this would be x1 and this is x2, okay? You're not allowed to have either coordinate go negative. So what ends up happening is this whole area over here, this is all equal to infinity. It's like there's an infinite wall, okay? So is that function convex? It's, okay, let me ask you a simpler question. Imagine you have a function, I don't know, h of x equals 0 for x greater than 0, greater than or equal to 0, and equals infinity for x less than 0, okay? So the function is like infinity. I don't know how to draw infinity, okay? It's infinity here, and then it's 0 there, okay? Is that function convex? Well, let's apply the definition of convexity. So if we have 2 points, so you say a point here and here, okay, A and B, okay? And if we connect, if we take the convex combination of this point and this point, is it greater than or equal to the function in between everywhere? Well, so f of h of A equals infinity, right? And h of b equals 0, right? And lambda times infinity plus lambda times 0 is equal to what? By the way, lambda is in the interval 0 to 1. Everybody's looking at me like they're like freaking out. It's equal to infinity. So you might say, hold on for a second. Nobody ever told me that before, okay? Well, here's the thing. You can add infinity to the real line for you. So you can make infinity a member of the range for your function. But you just have to define what the rules are going to be. And the rules have to be consistent. So infinity times any real valued number, including infinity, is infinity. Infinity times 0, you can't do. It's like not defined. Okay? And, you know, I think you can figure it out from there. So you can come up with a consistent system that includes infinity, right? And then according to that consistent system, then this is infinity. So every point along this line is greater than or equal to infinity. No, it's less than or equal to infinity, because infinity is less than or equal to infinity, of course, right? So therefore, I mean, these are all the rules you have to make up, but then you impose them, and you just make sure that they're self-consistent, that you don't have any self-contradictions. And then this is convex. So the whole reason that, so they go through a lot, the constraint optimization people worry about these things a lot. Actually, a function like this is called, it's called proper enclosed, I think. I should know the terminology for this. And they usually they worry about these things. So if you write theorems on these sorts of matters, people worry about it. Okay, but anyway, so my point is just that this is legit, okay? And so this thing is convex. This is convex. So this is convex. It's not strictly convex, but it's convex. Okay? Okay, so now let's see. So the proximal map, so what's f of x going to be equal to? It's going to be the argmin over, or f of v, say. It's going to be argmin over x of 1/2 y minus ax plus x minus v squared, right? And this is a over 2. So I guess I can differentiate this. I think the solution comes out that this has got to be equal to, it's got to be equal to, it comes out to like v plus y minus af. So I'm doing this in my head, guys, times A transpose A plus A plus A times I inverse. Hold on. Okay, I'll let you do the computation, but I claim that this is the answer. Write that down. That's the answer, I'm pretty sure. You can double check it. So intuitively, well, first of all, this is a quadratic function, so if I differentiate and set it equal to 0, I can calculate an answer, right? Okay. If y minus ax is 0, oh, this isn't ax, this is v. Okay. X isn't. So if y minus av is 0, then the solution is going to be at v. Okay. Okay, you can think about this for a while, or you can just calculate it, and I think it comes out to be correct. This is kind of like regularization here. As a matter of fact, that's called, I think, ridge regression when you're doing least squares optimization. So this is like doing ridge regression on the back projected error. Okay, so that's the solution. Actually, you probably can't really compute it this way anyway. You have to do an optimization. But it's nice that there's a closed form answer, okay? Now, what about H? Okay, so that's going to be equal to the arg min over x of h of x plus a over 2 norm of x minus v squared, right? What does that mean? Okay, so it's like I got a point over here. This is x1 and this is x2, okay? All right, so I pick a point. If this is B, the input, right? Then what's the solution to that optimization? It's just V, because if V meets the constraint that if it's positive, if its elements are positive, then the value of, let's say this point was in here, this answer was in here. What's the answer in that case? V. The answer is always V, right? Because the value of x, which minimizes the difference between the distance between x and V, is V, right? It's kind of trivial, right? Does everybody see that that's trivial? Now, if I put H here, H just says I'm not allowed to have solutions with negative components because that would screw me up, right? So I have an infinite potential to keep me away from there. Okay? It's like I hit a wall, quite literally. Well, not literally, because I guess, but it's quite figuratively. I hit a wall, right? Because what happens is that this is a wall over here. If I see what I'm saying? Okay. Now, but I'm within the wall, so I'm good. So the output just comes to be V, right? So I'll call this V1. So H of V1 is equal to what? V1, right? Now, what if I have V2 here? Then it's asking me, what's the minimum difference? What's the point in the feasible set? This is called the feasible set. That has the minimum distance to V2. What's the answer? It's here, right? I'll call that x2. So x2 equals h of v2, right? What if I have here? Oh, that's v3. It's going to be here, right? So that's going to be x3, right? So you can see what happens. So if I put h to some value v, right? What's it going to be? Well, it's going to be, I can actually, first of all, okay, because this is a Euclidean norm, the minimum distance point is the projection, basically, onto the feasible set. The feasible set's convex. So since the feasible set's convex, the minimum distance point to any convex set is always unique. By the way, there's a very interesting theorem, which is that a set is convex if and only if every point in the space has a minimum distance point in the set. It's if and only if. So if you have a convex set, there's always, for every point in the space, there's always a minimum distance projection. And if there's always a minimum distance projection, the set must be convex. And that's actually quite a subtle thing. I know I'm going off to a little tangent, but this is a very kind of beautiful little thing in topology. It's because a circle is sort of an interesting special case that violates that. Well, it doesn't violate it. Well, it doesn't meet the constraints. So circle, the literal circle, not the interior of the circle, but the circle, is not convex, right? Because, right? But if I take any point here, there's a minimum distance point, right? So but that seems like a violation of the theorem, because the set's convex if and only if every point has a minimum distance projection, a unique minimum distance projection. So what's the exception? There's one point that doesn't have a minimum distance projection, huh? The center. The center is the count. Doesn't have a unique minimum distance projection. So I don't know. I just thought that was interesting. Okay. Actually, circles are really interesting because they're non-convex sets, but you can find minimum distance projections onto them. And that's actually what happens a lot when you do phase recovery problems. Okay, so, okay, I'm a little off into a tangent. So the point is this. You have some point in this space. You have some point in the space. Now, how do you find the minimum distance projection onto the feasible set? Well, what you do is for each component I of that, okay, that component is going to be equal to Vi if Vi is greater than or equal to 0. But if Vi is less than 0, then what's it going to be? It'll be 0. So it's a very simple operation to implement. You can do this in, I'm sure that this is implemented in Python, right? Isn't this like the clip function? Is there a clip function in? Yeah, there's a clip function, okay? This is the clip function in Python, right? It's, so h of v is equal to clip v onto the interval 0 to infinity, right? Does that notation, I'm making that notation up, but it's more or less clear, right? So that's easy to do, correct? Oh, maybe I should have pointed out, I guess maybe I forgot to point out that the original problem's hard. The original problem is hard. Why did I write this twice? The map estimation, x hat, is equal to arg min over x of f of x. It's actually, this is going to be 1/2 y minus ax norm squared plus h of x. This is so-called, this is quadratic optimization with a positivity constraint. This is actually a pretty hard problem to solve because so you might think what you would do with a problem like this is you solve the problem without the positivity constraint. And then after you take the solution and you just clip any of the negative pixels to be 0, right? Except that's wrong. That doesn't give you the optimal solution to the problem. People following what I'm saying here? Okay, why doesn't it give you the optimal solution to the problem? I'm running out of Blackboard space. I'll draw it down here. I don't want to confuse you, but because, okay, see, this is the feasible set over here, right? So I'll draw the feasible set with a crosshatch. That's maybe not the right way to do it because I want the solution in the crosshatched area, okay? Well, what'll happen is, let's say that your cost function looks like this. So the unconstrained solution falls there, right? So if you clip the unconstrained solution, you get this, okay? But the constrained solution falls there. So if you have a highly ill-conditioned problem and you put positivity constraints on it, you don't get the same answer by just clipping. If you solve the unconstrained problem and just clip it, you don't get the same answer as if you solve the constrained problem. And it can be very significantly different, okay? Intuitively, it would be like if you let pixels go negative, I mean, there's interactions between the pixels. That's the thing that's the point, okay? So if you if you constrain the pixels all the way positive, or the non-negative, then you're going to get a different solution. You're going to get a subjectively different solution than if you let the pixels do crazy things and then just clip them off, okay? Does that make sense? Are there any questions about that? Okay, so my point was just that the constrained optimization problem is not easy. We actually, in the notes I mentioned it, I think, there's this thing called the KKT conditions, right? But, you know, the KKT conditions are fine, but they don't really tell you much about how to solve the problem, okay? They're just some conditions, but what do you do, okay? I'm going to use this to give you an algorithm to solve the constrained optimization, the quadratic optimization problem with positivity constraints, okay? Okay, so I have a simple implementation of H, right? F I can compute in closed form if I feel like doing this. If not, I can solve it with any kind of quadratic optimization problem, any kind of you know, gradient descent or something like that, conjugate gradient. Now I put it in this iteration here, and this is guaranteed to converge. So what is that going to be? The board's getting a little messy. I apologize. How about if I erase this? I kind of want to leave that up there because that defines the proximal maps, right? I guess I'll erase this. And then this is the actual ADMM algorithm. The beauty of this is that when we write this out, you're going to see it kind of makes sense, okay? It's intuitive that it seems reasonable. Okay, so what you do is this. You take, so what's your solution? Repeat what? So the first thing you do is you compute x of v minus u. So, oh, I didn't write, oh, okay, so f of x, or f of v, is equal to v plus a transpose a plus ai inverse a transpose y minus av. Okay? I'm not even going to write that because it's too complicated. I'm just going to write that it's x goes to f of v minus u. We initialize it with, say with, you know, without loss of generality, this is 0, and v, say, is 0. It doesn't have to be 0, but let's just take it to be that, okay? And then what you do is you say, okay, you say clip, and when you clip now, you have to clip x plus u. So you take x plus u, and you clip it to the range 0 to infinity. So you take x plus u and you check to make sure, you clip it to be positive. Now x and u can both be negative, but there's some at every coordinate you have to clip to be positive, okay? And you put that in v, okay? And then u, you set to u plus x minus v. So x minus v, so this is x plus u, and you clip it to be positive. So you clip off any negative amount, right? So, and that's v. So, how do I put this? So if you didn't clip it, this would be, v would be x plus u, right? So if you subtract x minus x plus u, this would be just minus u. So if you don't clip it, you get u minus u. It doesn't change. It's 0. So the increase in u is just the amount you ended up clipping off. So basically, what happens is that intuitively, okay, I'm going to try to explain this. Intuitively, if the pixels try to go negative, what you do is you attach a spring to that pixel, and you start pulling it up. until it becomes 0 or positive. So this algorithm is guaranteed asymptotically to converge to the global minimum to the constraint optimization problem. So this is as far as I know, I mean, I'm not sure what I'm saying is precisely stated enough to be a true statement, okay, or a false one. But as far as I know, in a qualitative sense, this is the best algorithm for doing constrained solutions to enforcement of positivity constraints for constraint optimization. This is like the state of the art. There could be like, there's a thing called quadratic programming, which I'm not like super familiar with, but and this is a solution to a quadratic programming problem. But the quadratic programming problem, there are special techniques for low-dimensional cases which might beat this, okay? Or you can maybe converge this converges asymptotically, but maybe converge in a fixed set. There's a lot of body of literature on quadratic programming. That's what I'm really trying to say. But for practical problems that are large dimensional, like reconstructing images, this is the state of the art. Because implementing positivity is not easy, okay? Now, okay, good. Did everybody understand that? Are there any questions about that? Because that's a relatively simple case. I want to try to do a more complicated one next. Okay. There's other things you can do, okay? So I want to write this, repeat, because this is the basic algorithm oh God, I'm going to go through this again. X goes to f of v minus u, and then v goes to h of x plus u, right? And then u goes to u plus x minus v. That's the algorithm, correct? Now, okay, so f, let's just say quadratic, some quadratic optimization problem. It doesn't even have to be, it could be any kind of convex optimization problem. But let's take the other possibility that we have h of x is equal to, say, the sum over some various pixel pairs, okay? Uh-oh, you're getting nervous again. You're like, this is the notation from the earlier chapters of the homework problems were giving me a headache. Don't panic, okay? So bij, right, times what I can take is xi minus xj, like this, okay? So this is an example of TV regularization. Right? Now, TV regularization. So that's total variation, right? I want to point something out which is very important and is subtle, and I know you guys are going to go like this. You're going to pretend you understand what I'm talking about. You may not really. You're pretty good at deceiving me about stuff like that. Okay, so my point is this. I can write H in the following general form. I take X, I multiply it by some matrix B, okay? And I take, say, I take the L1 norm. Why can I write it like that? Because if you think about it, well, first of all, I could have done this. I could have taken this like that, right? So my point is that for every entry in this sum, I can find a matrix, right, with, how do I do this? Okay. For every, so the way I can do this is I could do it as the sum over I, and then the sum over j, right? And then I can make this the absolute value of bij times xi minus xj, like this, right? And so I can write that like this, and then I can divide by 2, because then I'd be hitting each pixel pair twice. So this looks like a so basically you have I'm not doing a very good job at this. Oh, no, let me not write it like that. I can make it the sum over I and j of the absolute value of bij of xi minus xj, right? So now, if there are n pixels, I can form a matrix B, okay? And the height of this matrix B is going to be n squared. So I have a row for every entry, every pair of pixels, okay? And then the width of this thing is n, okay? And the output for some pair, from pair pixel, the ijth row, it's really a tensor, okay? Which is the confusing part. The ijth row of this matrix is B, the ijth row, and then jth column. Oh, yeah, I'm not doing a really great job. I got to work on how I could explain this. Do people see that you could do this? Maybe not. The entries of this matrix is very sparse, because it only has entries. Basically, if you have the image, right, usually you're just taking adjacent pairs, right? So what will end up happening is that the 2 entries associated, for each row, there will only be 2 non-zero entries, okay? And then you also have to multiply by the associated bij. Because I'm including that in the matrix weighting. Does that make sense? That make sense? Okay. Now the L1 norm of the result, just remember the L1 norm of, say, z is defined as the sum over the absolute value of zi. So that takes care of that, right? So my point is that you can write TV regularization in this form.